from today, I guess you're gonna see me for at least a few weeks. We're gonna cover some more like supervised learning algorithms, and we're gonna talk about deep learning, and then I'll pass on to Chris to talk about unsupervised learning. So I think I'm going to be in charge in the next 3 or 4 weeks. And I'm going to use the board partly because I think there's a little bit more memory on the board, right? Like I can write, you can review things that I can see. I wrote like 10 minutes ago even. I don't know whether that's the best for everyone. I think in the past I've surveyed students and someone preferred the board, someone prefers the Zoom, the iPad. So I'll give it a try with this. But any comments or any kind of suggestions are welcome, and we are open to change the format as well. So, but for today, at least I'm going to use the board. And I think the video is able to capture the board almost the same as the iPad, I hope. Okay, so I'm going to talk about the so-called generative learning algorithms. So the next 2 lectures will be about this. I'm going to define what does it mean by generative learning algorithms. And there are 2 types of generative learning algorithms that we're going to cover. One is called Gaussian discriminative analysis. I guess these are all new words that I have to define as I'm introducing these things. GDA. And another type of algorithms is called naive Bayes. Okay, so I guess let me get started. So I'll start by defining what do I mean by generative learning algorithms. To kind of define these terms, I think it's useful to compare with what Chris has introduced in the last 2 weeks. So in the last 2 weeks, I think the type of algorithms Chris introduced, we call them discriminative learning algorithms. So discriminative learning algorithms. So the reason we call them discriminative learning algorithms is the following. So in some sense, the definition is that if you model or you parameterize the relationship, the conditional relationship of y given x, then we call this discriminative learning algorithms. And I think, if you recall, this is the type of algorithm, the type of kind of models we considered in the last 2 weeks, right? So we model y as a linear function of x, maybe y is linear function of x plus Gaussian noise, or maybe y is linear function of x plus a exponential family, or something like that, right? So for example, in the most general form, I think the last 2 weeks can be summarized as you think of the x, the y given x parameterized by theta. This is a distribution of y given x parameterized by theta. You write this as some exponential family, some distributions in exponential family with some parameter, with some input eta, and this eta is a linear function of x, right? For example, you can say this is a Gaussian distribution with mean eta, and that's just the standard linear regression, right? So this is why we call them discriminative learning algorithms. And today we're going to talk about the so-called generative version, generative learning algorithms. The basic idea is that you are going to model or parameterize. Here, model is a word, basically means parameterize, or you have a mathematical model for the joint distribution P of x, comma y. The joint distribution of x and y, using the simple chain rule, you can write this as x given y times P of y. So you model both these 2 quantities. Is this there's some light is flashing, right? Are you bothered by it or not? I'm fine with it. Just okay, no worries. Okay, I think it flashes after every minute or something. Anyway, so you model the joint distribution by modeling each part of this too. And particularly, you model the joint distribution by modeling the distribution of y and the distribution of x condition y. Here, x and y are not symmetric. Y is the label, x is the input. And typically, they have very different meanings. So y could be something like, the price of the house, and x is the features, what you know about the houses, right? So like the square feet, the lot size, so on and so forth. So, and recall that x is the input, or and this is maybe something like a label or some kind of class, right? If you have classification, this is about class, like maybe positive sentiment, negative sentiment. And so basically this is the distribution of the input given the label, and this is the distribution of the label itself. And sometimes we also call this, a prior for the label, a prior for the class or the label. Because this is what you believe, like for example, suppose y is 1 means positive sentiment, y is 0 means, negative sentiment, right? Suppose you are classifying the text. Then this is a distribution over 2 labels, right? Positive and negative. And this is the prior that you have for how many positive examples or negative examples are in your data set. And then, so after you model and parameterize this, you can learn these 2 distributions, right? You can learn the distributions, learn P of x given y and P of y. We're going to say how do we learn them. And after you learn both of this, you are going to still solve the classification problem. Your goal is still the same. You are trying to classify. You are still trying to compute. So this is the test time. You are still trying to compute, for example, P of y given x, right? You're still trying to classify what's the chance of each of the label. Or you probably want to get the max of y given x. We're going to talk about exactly you care about. But essentially, you still care about the relationship of y conditional x. And how do you get this? You get this by Bayes' rule. Meaning, so recall that P of, for example, y given x is equals to P of x given y times P of y over P of x. So you know this quantity, and this. I'm assuming you already learned this too, right? And how do you know the denominator? Then you can just write this as the denominator is really just you take sum over y, P of x given y times P of y. Maybe just for the sake of notation, let's call this y prime. Right, so this is the standard, this is the called total law of probabilities, where you compute the marginal probability of P of x, you use as the denominator, and then you also use these 2 quantities on the top. Actually, in many cases, you don't necessarily have to compute the P of x. We'll see exactly how it works. But roughly speaking, after you know these 2 things, you can know, after you know x given y and y, you can know y given x by doing some Bayes' rule. By the way, feel free to stop me at any point, just raise hand or just speak. Maybe you first. Is it true? So let me repeat the question. Is it true that the discriminative learning algorithms cannot work on non-discriminative exponential family? No, I think the discriminative learning algorithms can also work with other possible distributions here. So as long as you specify y given x and you parameterize that by some parameter theta, in theory, you can still learn them using similar type of methodology. I'm going to discuss the methodology as well. But if you have exponential family, then it's going to be, there are several benefits. For example, Chris discussed this many properties, nice properties of exponential family. If you don't have them, then you cannot use those properties. You have to use something else, or you have to rely on optimization, or sometimes it's challenging, depending on the cases. But in principle, you can have other distributions here. Yeah, maybe let's just do this order. Yeah.
What exactly are you doing? It's possible to give an example of how it's being used.
Yeah, I'm going to talk about that.
So,
This is just a general framework.
yeah, so the difference between the two that I can guess is that on this in discriminative learning algorithms, you have a parameter that you're trying to learn, and here you don't, and here you don't have any parameters, right?
You will have parameters because I'm going to parameterize these two distributions and learn them. So yeah, I'm going to talk about that as well.
This is more circuitous path to coming to the same kind of P of Y given X, right?
So this is yes. So I'm also going to discuss the differences. Why, like, what's the high level differences? Why you want to do this? But I think it's easier to discuss those. Once I tell you a little bit more about concretely how this works. But so far, you are right. Basically, this is a somewhat seemingly circuitous way to get P of Y given X. Right? It's not direct. Right? Yeah, I think I'm going to discuss that, discuss the differences, probably later in the lecture, just because, it's easier when I have some examples. Okay, any other questions?
So would it be possible to write a little bigger, please?
Sure, yeah, that's a great suggestion. I think that's probably also useful for the recording as well. And also feel free to remind me again, because this happens to in the past as well. Like every time after like a few lectures, I stopped writing big. Even after a few minutes sometimes. Maybe. Okay, so this is just a very high level introduction. So we're going to talk about two instantiations of this general idea. Instantiation. So one is called this. So the differences is really just in one case is a continuous x, and the other case is discrete x. So this continuous x is called the Gaussian discriminant analysis, and for the discrete x we are going to focus on an application which is the span filtering. Right. So and today I think we're going to mostly talk about the continuous case. And next lecture, I'm going to talk about the span filtering. All right. So now one example. How do we instantiate this plan? So for GDA, what you do is you say, I'm going to suppose X in RD. I'm going to drop the convention. Just because here I'm not going to use the bias. At least in the modeling part, I'm not going to use the bias. Don't worry too much about it. It's just we don't have the x0 is 1. I know it doesn't really matter that much. So so the main thing is I'm going to assume. You can say this is assumption. You can say this is a modeling assumption. I'm going to assume P of x given y is a Gaussian distribution. So what does that really mean? That really means that you write this, you say x given y is following some Gaussian distribution with some mean and covariance. And here note that x is a high-dimensional vector, so I'm going to have a high-dimensional multivariate Gaussian distribution. So and with some mean and with some covariance sigma. So I think it used like it's probably useful for me to briefly kind of digress a little bit to briefly talk about some basics about multivariate Gaussian distribution. These are just some very quick review if you haven't seen this. But I'm assuming that you know something about one-dimensional Gaussian distribution. So just a very quick digression. So if you have a multi-dimensional Gaussian random variable, so what happens is that you suppose you have some random variable z sampled from this Gaussian distribution with mean mu and sigma covariance sigma. So here mu is a d-dimensional vector and sigma is a matrix, is the so-called covariance matrix. So, and the definition, so the property you need to know is that, as the name suggests, the expectation of the z is supposed to be the mean of the mean parameter, right? So, and the covariance of the random variable z, which is defined to be the expectation of z minus expectation z times z minus expectation z transpose. This is, is the covariance matrix. So this is how you generate this z from this Gaussian distribution parameterized by these two parameters, mu and sigma, and the resulting random variable z would have these two properties. The mean is mu and covariance is sigma. And you only need two set of parameters to describe uniquely a Gaussian distribution. And you also know that you also know the density of this Gaussian distribution. So the density of the Gaussian distribution is something like this. I don't expect you to remember the formula because now I remember it after I teach it so many times. But before I taught it, I don't think I remembered it in my graduate school. But the formula is that, I'm not sure whether you can see this, something like this. And here, this is the determinant. Okay, great. I see some question. Sure, maybe I'll start with the one.
What does the denominator say?
What is the denominator?
The denominator,
So this is 2 pi to the power of d over 2, and the determinant of sigma to the power of half. I'll write even bigger.
And then what is the little triangle over the equal sign?
Oh, this is just the, why I'm doing this? Oh, this is just a definition of the covariance, in case you don't know the definition. So,
okay, thank you.
Yeah, I'm just using that as to indicate this definition. And by the way, this formula, I don't think we really have to remember it. The most important thing is you have a constant times some exponential of some quadratic form of z.
So is
Z is a vector. Yeah, that's a good question. So this is why this is a little more complicated than one-dimensional case, right? If you are familiar with the one-dimensional case, then this will be still a scalar mu, and this will be a non-negative scalar. Sometimes people write a sigma square, right? So, and the sigma will be just so for one-dimensional case, this is just the variance, and now it's the so-called covariance. And I guess if you are so it's in some sense, if you look at sigma of ij, this is really just the correlation between will be the expectation of zi, say the i's coordinate minus ui times zj minus mu j. In some sense, the entry of the covariance matrix is capturing the correlation between two coordinates. Of course, you have to remove the mean to match the correlation in the right way, but you match the correlation of the two coordinates of this random variable. I saw some other questions. Yes, so x and z are the same thing here. I use z because I want to be abstract. So later I'm going to have a little more. I'm going to have to change this a little bit. Yeah, but this is just for abstraction. I use a different variable. The second term is sigma. Here. So here, because they are scalars, so that's why I didn't have the transpose. So this is a scalar, this is a scalar, right? And here, the reason why I have transpose is because I need to make a matrix. So I don't know. I think some of you probably are familiar with this, so I want to spend a lot of time on this, but some of you probably not very familiar. So I think I used to have some, let me show you some other pictures to get a little bit more sense on the covariance. Let me see, how do I connect to this? Maybe, do they know this? How do I signal anything to them? I don't see they are capturing the video, the screen. Anyway, these are in slides, so it should be. Oh yeah, okay, great. So it used to be the case that I make slides for this part of the talk. I just make 3 slides, but then I realized that maybe it's just easier for me to show you the lecture notes because then you know where to find them again, right? So I'm not being lazy here. It's just it's also easier for me, of course. Okay, so these are some visualizations of the density function here. So the first set of just look at the figures. This is a 2-dimensional case, right? You have these two, and you visualize the density of this of the Gaussian distribution. So density, always look like something like this, right? So and these are the cases where the covariance is identity. It means that when the covariance is identity, it means that when the covariance is identity matrix 1, 1, 1, 1, it means that there's no correlation between any pairs of coordinates, right? Like I and j, when I and j are not the same, they have no correlation, and the result, the kind of the shape of this Gaussian is always spherical. So basically, when it's identity, it means that you have equal strength in all the basically you just have the same strength in all the directions because every dimension looks the same in some sense. So basically that's when you see this kind of very spherical shape of the density function. And then you can the one thing is that the size of this density function depends on the scalar in terms of the identity, right? So if you have identity, then I think this is the leftmost one. But if you make the covariance 2 times bigger, then your density function will be supported on, in some sense, mostly supported on a larger region. So I think that's the last one. And then in the middle one, you have a smaller covariance. So in some sense, the covariance is describing at least how large this the shape of this density function is. And also it's declaring 2 things, right? One is the size, and the other thing is that what's the correlation, what's the kind of orientation of the shape. So maybe one way to think about this is that if you look at the second rows of the figures, so these are cases where the covariance matrix are no longer identity. And they're, for example, in the third figure here, you have some correlations between 2 directions, and then you see this this ellipsoid kind of shape is rotated into that direction. Just because in that direction, the 2 coordinates are more correlated, so it's more likely that these 2 coordinates are simultaneously bigger or smaller. So that's why in that direction you have more kind of mass in that direction. And you can see that the differences between these 3 figures is that the correlation along that direction is bigger and bigger. In the first one, there's no correlation in that special direction, x is equals to y direction. And the second one, you have a little correlation, so that's why it tilts towards that direction. And then in the third one, you have more correlation, so it's even more skewed in some sense. Any questions? So I guess maybe another way to look at this is that you can look at the contours, right? Of this thing. So basically, you look at the level set of this density function. Level set means that the set of basically the set of points with the equal density, right? So and then you can see that you get this kind of ellipsoids, and the same thing, right? So if you have more correlations, then this ellipsoid will become more tilt towards one special direction. So for example, here, I guess if you can see my pointer, so this means that in this direction, so I think if this is x1, this is x2, right? So if you see these kind of contours, then it means that x1, x2 are likely to be simultaneously bigger or smaller. And so that's why they have correlation. And if you see in this one, then you're going to have some reverse type of things, right? So if x1 is bigger, then x2 is likely to be smaller. And that's when you see this kind of shape. There's no need to, exactly, like understand this, right? So like, it's just some kind of rough intuition, in reality, you don't necessarily have to exactly, visualize all of this, but these are, any questions? I know sometimes this could be confusing. Sometimes this could be very enlightening. I don't know, like, depending on, feel free to ask any questions. Okay, so I guess we'll move on back to the more mathy stuff. Okay, cool. So I've introduced the multivariate Gaussian distribution, and now I'm going to go back to the Gaussian discriminative analysis. So we are going to parameterize x given y as a Gaussian distribution. So by the way, I think I forgot to mention that here, in both of these two cases, the y is always discrete. You can make y non-discrete as well, but here we're only looking at a case where y, the label, is always discrete. So now let me continue with the GDA. So as I said, y is discrete, and we are only going to assume that there are two labels, say 1, 0, and 1. 0 could mean, for example, I guess, I don't know why. Oh, I think I missed one small thing here, but let me just. So I guess one of the running examples we used to have for this GDA application is that you can think of like you have some kind of like I guess for example cancer classification. So like a benign or malignant classification. So you have some maybe x1, x2, two-dimensional inputs, and you see a bunch of data like this. So these are cases where you have benign cancer. Think of maybe x1 and x2 are some measurement, right, of the patients, right? So maybe blood pressure or some size of certain kind of tumors, and for every patient or every case, you know whether this is a benign cancer or not, right? These are the bad case, right? Malignant cancers. So and the question is that you want to kind of classify these, right, examples into two classes, right? So that in the future, if you see one more example here, maybe you want to know whether this is a benign one or not. And the label is basically here. Let's call this label 0 and this label 1. Right. So that's kind of the target applications we are thinking about. So now I'm going to parameterize what is x given y, right? X given y. And I need to specify two cases, right? One case is that what is the x distribution of x given y is 0. And the other case is that what's the distribution of x given y is 1. I'm going to make both of these Gaussian distribution. So I'm going to assume that x given y is 0 is a Gaussian distribution. And the Gaussian distribution has mean mu0 and covariance sigma. So here I'm in a high dimensional case. So mu0 is in Rd. In this case, D is 2. And sigma is in Rd by D. And for the other one, my modeling assumption is the same. I'm going to assume this as mu1 and sigma. Okay, so the same covariance, that's just for convenience. I can use different covariance matrix. But here, I have to use a different mean because clearly, if you fit a Gaussian distribution to this bunch of points and you have a Gaussian distribution for this kind of points, you're going to have different mean. Right? So that's why I'm going to have mu1 here and mu0 here. So mu1, mu0, sigma, these are the parameters. Oh, yeah, go ahead. Yeah, so this is mostly just for convenience and for, like, you can make them not the same covariance matrix, then in terms of like the optimization, in terms of learning these things, is going to be more complicated. So it's still learnable, at least with some advanced techniques, but it's going to be more complicated. So here is really, in some sense, a simplification, simplified assumption.
This probability of x given y equals 0 or probability of x given y equals 0?
Oh, yeah. So that's a good question. So this is like this. So if given this event y0, what's the distribution of x?
Yeah, I still didn't get why you separate them into two distributions. Like, is it because they are really different in the graphs that you draw, or is it some other reason?
Right, and that's a good question, right? So how do you model the x given y, right? So in many cases, you have many different choices, right? You can have different covariance, you can have different means, or you can even model them in different ways. So here, I think at least if you look at the data, you see that the distribution of x given y is 1 and x given y is 0 sounds quite different. So probably it makes sense to model them separately, right? If you model the whole thing as a joint Gaussian, I think it doesn't look like a Gaussian. That's pretty much the reason. Okay, cool. So are we done? So we haven't done with the modeling yet because we only model x given y, right? Before, remember that we also have to model p of y, right? You need the p of y and p of x given y to know the joint probability distribution, and then you can use the Bayes rule. So how do we model the p of y? This is relatively easier because p of y is only a distribution over two possible choices, right? Y only have two choices, 0 and 1. So basically, you just have to have two parameters, right? So one parameter is supposed to model p of y is 1, let's call this phi, and then you have p of y is 0, let's call this 1 minus phi, because the sum of these two has to be 0. Sum of these two has to be 1. So, and so in some sense, you say y is from this Bernoulli distribution with parameter phi. This is just another way to say this. Okay, so basically in summarize, what are the parameters? So the parameters, I guess this goes back to the question, someone asked this question, right? So we do have to have parameters, even for the generative learning algorithm, and the parameters are mu0, mu1, sigma, and phi. And our next step would be, we want to learn these parameters so that we know p of x given y and p of y, so that we can compute p of y given x. Okay, so the next part is about fitting parameters. Okay, so how do we learn the parameters? From data, right? So we learn the parameters. The general principle is maximum likelihood. I think probably Chris has talked about this word maximum likelihood, probably once or twice in the previous lectures. But here the maximum likelihood is a little bit different. I'm going to compare what's the difference between this likelihood from the one that we discussed before. So first, let me define what maximum likelihood here means in this setting. So by maximum likelihood, I mean I first have to define likelihood. So likelihood is this basically the chance of seeing a data given the parameters. So it's a function of the parameter. So if you have these parameters, phi, mu1, mu0, mu1, sigma, you can define the likelihood of these parameters. This is the chance of seeing all your data given the parameters. So you hypothetically think that all the data are generated from this distribution, and you look at what's the density of your data under these parameters. Sorry. Oh, even bigger. Okay. Yeah, sure. Thanks. So, and let me also clarify the notation here. So, x superscript I think probably Chris defined this, right? So we're going to use this throughout the lectures. So xi, yi this is the ith example. So we have this data set with n examples. I'm looking at the likelihood of all of these examples under the parameter phi 0, mu 0, mu 1, and sigma. So for every parameter, you have a likelihood. And this likelihood can have, this sounds like kind of complicated, but actually you can somewhat simplify it a little bit because these examples are independent, right? So you assume that your data are drawn independently from, each examples are drawn independently. So then you can factorize this. So this is the product of the likelihood of all the examples because you use the independence. P of xi, yi, given and you can even factorize this a little bit more to say that you can use the chain rule to get P of xi given yi and the parameters and times P of yi given the parameters. Note that not everything depends on everything else. Okay, I don't think I have a different color. So here you can have some simplification because yi, the distribution of y, only depends on phi, right? The mu1, mu2, mu0, mu1, and sigma are describing the conditional probability, right? So y only depends on phi, so you don't have to write here these things, right? Because they are there is no such dependencies. And also the same thing, xi condition yi only depends on mu0, mu1, sigma. It doesn't depend on phi, so you don't have to necessarily write phi here. Even though you write it, it's the same. So, okay. So this is the so-called maximum likelihood. And what you do is you want to say, I'm going to maximize this L, phi, mu0, mu1, and sigma. So basically you say, I'm going to maximize, so the learned parameters will be the maximizer of this likelihood function. You want to find a parameter such that the likelihood is the largest. So this is the so-called maximum likelihood in our context.
While you're making this independence assumption, isn't it possible that there is like some kind of dependence between the data, and in that case, what do you do?
Right. So why the question is why you make these independence assumptions? I think in short, if I have a very short answer, I think this is almost like always assumed in all machine learning settings, even in the most advanced settings. And the reason is that I think there are multiple reasons. You can say this is in some sense, one thing that you can imagine is that you do collect data somewhat independently from a very large pool. That's probably the simplest way to say it. Of course, there are cases that this independence is not true. For example, if you have interactions. For example, suppose I first get some data from you, and then I do something, and then I get some other data from you. And maybe these data are no longer independent. Or maybe the second time you provide me data, you also look at the first time. Sometimes, there's something about this dependencies, especially in reinforcement learning, like where you have interactions. So in those cases, we will drop this kind of independence assumption. But in most of the cases, we do assume the data are sampled from a large pool independently.
Phi is a scalar, right?
Phi is a scalar. Yes, you are right. And phi is a scalar and is also a scalar in zero. That's a good question. Do you have the freedom to change phi?
Yeah.
So phi is a parameter, right? So you're going to learn phi. You're going to learn what is the right phi from data. So how do you learn phi? So you're going to find out the maximizer of this, and the maximizer will be.
When we have, for example, some training data, isn't it just phi is equal to the cases when y is equal to 1 divided by the whole computation?
You are exactly right. You are ahead of me. Yeah. So, but we are going to prove that we are going to show that that's actually the solution. So there's a reason for that. You have the very good intuition, right? The phi is pretty much the proportion of the positive examples, or the proportion of positive examples, right? But we're going to actually show that's actually the case if you use this methodology.
Yeah. Can you just repeat in maximum likelihood or maximizing the chance of the data given the parameters?
Right. So the maximum likelihood is you are maximizing the chance of the data given the parameters. So the parameters are just you look at all possible parameters and you see which parameter can give the most likelihood. Oh, right. And so yeah, like this. So this is the maximum likelihood. This is the methodology we're going to use for generative learning algorithm. Not only today's algorithm, but also for next lecture, where we have other settings, we still maximize likelihood. And just to compare this with the discriminative learning algorithm, there we also use maximum likelihood. But the meaning of the phrase maximum likelihood could be a little bit different. So here you are maximizing the so-called joint, the joint density, right, of both x and y. You are maximizing the probability to see the pairs of x and y. But for discriminative algorithms, so for discriminative algorithm, so what you do instead is that you are maximizing the so-called conditional likelihood. Even though in many cases people just drop the word conditional when that is clear from the context. So and the conditional likelihood is this probability of seeing the family of labels conditioned on the inputs and the parameter theta. So, and you can also factorize this. You can factorize this as, so here I'm using theta as a generic parameter, just to be abstract, because I'm talking about the abstract setting, right? So you can think of this theta as the linear model family. So, and you can still factorize this. You can factorize this into using the independence. But whatever you do, you always condition on x. So x is considered to be in some sense, a deterministic quantity you observe. You don't know how x is generated. We don't care about how x is generated. You just care about how y is generated, conditioned on you see x. So, and part of the reason why you do this is that you only model y given x. You didn't model what's the distribution of x. So there's actually no way you can do this maximum likelihood above in the discriminative sense, because the only thing you model is y given x. That's the only quantity that you have a parameterized form for. So you just go with whatever you have in some sense. Right, and it turns out that these two are indeed different. There are some relationship and there are differences, which I'll discuss after I introduce more examples, I think. Any questions so far?
So this is what we've been doing so far.
This is what in the last 2 weeks, exactly. And maybe I think I think this is probably the best discussed after I give some examples from the concrete examples. But in some sense, you can see the differences between these two kind of algorithms and the differences between these two type of assumptions is that here you have more assumptions on all the data, right? You are making some assumptions on both x and y, and here you're only making assumptions on y given x. So it's really about how the differences will be about how many assumptions you impose on the structure of your data. How much, in some sense, there's a whole universe, right? So you cannot model everything, right? So you choose some part of the quantities you can model, and the decision here is that you model both x and y, and decision here is you only model part of it, and that will cause some differences in certain cases.
So in a generative learning algorithm, we have the assumption about the distribution of our features. So wouldn't that cause generalizability if you don't see the data set?
Right, that's a great question. So the question was that here for the generative algorithms we have assumptions on the features, right? Would that be a problem if you generalize to other examples? So it depends. it depends on whether your assumptions are correct or not in some sense, right? If your assumptions on the features is kind of Gaussian, then actually it would provide you more generalization because your assumptions are correct and it impose structures. And when your assumption is wrong, then it would cause problem. So actually this is this is basically like the main differences, right? So you for different algorithms, sometimes you can have as I said, you have a lot of variables in this world, right? So you probably can even pick some other, so basically you have you can try to model a lot of mechanisms, or you can try to only model a part of it. And what's the decision? Often it's a trade-off. If you model too much, then you are risking to model them incorrectly, right? And if you model too less, then you don't have enough, you don't leverage enough prior knowledge in some sense, right? If, for example, if you really know this is a Gaussian, you probably should leverage the prior knowledge. But you may be wrong. So it depends on the cases. Yeah, this is great questions. And I'll discuss a little bit more about this on a more mathematical level.
Do you use the Gaussian because given mean and variance and you don't know anything else, it's the best way to model something in real life?
Yeah. So I think the question is, given the mean and covariance, if you don't know anything else, is the Gaussian the best? Is that the question? Yes, I think that's a great question. So typically, you are basically right. If you don't know anything else, then you probably should just model them by Gaussian. If you only know mean and covariance. But on the other hand, to be fair, you know more than the mean and covariance, right? So for example, if you really want, you can compute the third order correlations between these data points, between these coordinates, right? So in theory, you can also, because you have so many data, right? If you have a lot of data, you probably can model other higher moments of the data. I'm not sure, the definition of moments. You look at the higher correlations between the coordinates of the data, if you have a lot of data. But Gaussian is pretty reasonable assumption, and it's still used very often. Sometimes people use transformations of Gaussian. So here we assume they are Gaussian. Sometimes people use, you can transform the Gaussian in certain ways. But Gaussian is pretty reasonable assumption.
So what about the generative method, why is the continuous value?
So how do we do the case when y is continuous? Is that the question? Yeah, so we're not going to cover that, but pretty much you follow the same methodology. You're going to have a different prior or different distribution for y, p of y, right? So maybe you can model p of y by, say, Gaussian again, if you want, or you're going to have more variables to describe the distribution. The accuracy.
Yeah, the accuracy will be
So I guess the question, in short, whether y is discrete or continuous, in some sense, is mostly decided by your data set, right? So I think typically if your data set is really discrete, right? So if you really just have benign cancer or not, right? You probably don't want to make it continuous for the same reason as you said. Why you want to make it more complicated, right? So you have more parameters to learn, right? But sometimes it's just your y is really continuous. There's no way you can discretize them or in a meaningful way. So, right. And also, to be fair, the parameters to model y is often much smaller. You have a much smaller number of parameters to model y than the number of parameters to model x. For example, here, if you count, so you only need one parameter to model y, right? So even this is continuous, you only need one real number to model y. Probably, if you have, say, for example, y is a Gaussian distribution, but it's one-dimensional, right? So you only need one parameter. But for x, it's a high-dimensional thing, so you have to always use more parameters. So typically, it's not a big issue.
Here you have only two features, so you could easily guess that we can have two distributions, one for when y is equals to 0, another one for when y is equals to 1. But let's say you have more features and it's kind of harder to visualize the data. I mean, how do you make this judgment of how many distributions to have on the parameters?
Yeah, I think that's a great question. How do you make this judgment? How many kind of distributions, right? So the easiest answer is that you always use two as long as you have two labels. If you just have two type of things you want to classify, you just always have two different distributions, two Gaussians. Of course, you may want to go more advanced, say even maybe for the benign cancers, right, it's not like really, really like all the benign cancers are the same, right? Maybe there's two subpopulations, right? So it does probably require a little bit domain knowledge, or maybe trials and errors. You could try to generalize this. Okay, so let me proceed with the. Okay, so I've discussed a lot of methodology so far. So now my next goal is, how do I maximize this? How do I maximize the likelihood? Right. So you need to be able to do this empirically, right? So to get the parameters, right? So this is about computation partly, right? So what we do is one choice is that you just write down this function in your computer and you run some optimization algorithm. But you want to do a little bit more than that in math, because that will simplify your implementation, right? So we're going to simplify this formula so that we can, and actually we're going to do a lot of math so that you don't really need a laptop to your computer to compute the parameters to run optimization algorithm for this, right? So what we're going to do is that so the first thing is that we know that if you do an argmax, so we care about the argmax, right? The maximizer of this thing. So the maximizer is the same if you transform your loss function with any continuous monotone function. So even if you add a log, the maximizer will be the same. And for the purpose of this course, we define this using a little l. This is the log likelihood. Okay, why we are doing this? It sounds like we just introduced something even more symbols. The reason is that this will make the product to a sum. So log of this product, log of a product of bunch of terms will be equals to the sum of the log of each of the terms. So this will be sum of the log of these two terms. And the log of the product of these two terms will be the sum of the log of each of them. So it will be log of p of xi given yi plus the log of p yi given, I guess I don't have to write phi here for this purpose. I can write phi here. Right, so everything becomes a sum. And that's very important, actually, because even you do this numerically, it's very important to take the log, because all of these numbers, if you do it empirically, you will see like they are either very small or very big. Just because, recall that when you have Gaussian distribution, there's exponential here. So it's kind of pretty easy to see the density function. It's pretty easy to be either very big or very small. They're never on the best scale, like you can imagine. But if you take the log of it, the scale will be much nicer. So the log of the density will be on like some reasonable kind of scaling, so that you can numerically use, and also it becomes a sum, so you don't have to do the product. So, and then how do we proceed? One option is that you can still do the numerical stuff, where you can do an optimization algorithm to get the minimizer. But here we can actually analytically compute the maximizer. So the maximizer here, how do you compute it? What you do is I'm going to continue here. So how do you find the maximizer? So there's a small fact. I guess probably you learned from the calculus class. So if theta is a maximizer, then that means that of some function f theta, I'm being abstract here. So then it means that the gradient of the function at theta, evaluate at theta, is equals to 0. So if you are in the maximizer, you have to satisfy the gradient 0. And actually, in many cases, if f is convex, then this is if and only if. If f is not convex, this is still a necessary condition. So for us, it's actually convex. So it's a necessary and sufficient condition. But for other cases, this might be just only a necessary condition. So because you have this, then you can solve the equation. So you can try to solve the equation. I'm going back to, this is a small abstract fact. Now I'm going back to this case. So basically you say the gradient of the loss with respect to all the parameters should be 0, right? So like with respect to phi, mu1, mu2, and sigma should all be 0. So basically you just have to say, right, the gradient is 0, and this really just means that the partial derivative with respect to each of the parameter is 0. So now you have 4 equations, and you can try to find the solutions for these equations. And this is, I think, homework 1Q1D. So in that homework, we're asking you to, first of all, you have to compute what is each of this is, right? So you have to have an analytical formula for each of this, right? So what is the derivative of L with respect to phi? You have to do some calculation to see what's the derivative. You have to plug in all of our definition of this p, these two p's, and you get the loss function as a function of phi, and then you derive the derivative with respect to phi, and then you write out that this is 0, and you solve the equations. So that's homework Q1D. And this is a little bit complicated to some extent, but not, it's still manageable. And this is, there are even more complicated things than this, in machine learning. This is still, but at the first sight, it would be a little bit complicated because all of this has a little bit kind of like complex formulas. Right. So, and what I'm going to do next is that I'm going to tell you what's the solution of this directly. So you know the answer of the homework question. And I'm going to proceed. I'm going to interpret whether the solution makes some sense. You will see the solutions actually make a lot of sense intuitively. And I'm going to proceed with that.
Think about the notation. Is it like earlier you were mu0, mu1, now you switch to mu1, mu2?
Oh, my bad. Mu1. Did I switch to that? My bad. This is mu0, this is mu1. My bad. Thank you.
The first one is a scalar, right? The other one is going to be vector.
So yeah, so what's the dimensions of this? Right. Yeah, that's a wonderful question. So I think often this is a confusion that is pretty often, like just because sometimes in math they have different things. So in this class, the derivative of with respect to the parameter, any parameter, will have the same shape as the parameter. So this is a one-dimensional parameter. So that means that this is a scalar. This derivative is a scalar. And this is a d-dimensional vector, mu0. So that means the derivative is rd. And this is in rd by d.
Only first zero is scalar. The other zeros are like one of them vector, other ones are...
Right, so this is 0 as a vector, zero vector, and this is a zero matrix.
Thank you.
That's good. Okay, cool. So I need to erase something, I guess. Okay, so what are the solutions? So the solutions are, okay, I'm going to first define some notations. So let U0 to be all the examples that are positive. These are the index for the positive examples. Indices positive. And wait, my bad. This is U1. U0 is the indices of negative examples. Okay, so under the MLE solution, the solution will be the following. So phi is equals to U1 over N, where N is the total number of examples. Which is equals to U0 plus U1. So what is this? This is really just the fraction of positive examples. Right, so this is the phi you learn. So phi is supposed to be the probability of y is 1, right? That's your modeling choice. And it turns out that if you learn it from data, it will be exactly the fraction of positive examples in the data. So this is the most likely phi that can generate your data, which is exactly the same fraction as in the empirical data. And of course, 1 minus phi will be the fraction of negative examples in the data. Question? Okay. How do I remember this? I have to burn this in my head. So 1 minus phi is equals to, this is the fraction of negative examples.
It's just, I can see it here. U sub 1 is equal to what?
Mu sub 1, U sub 1 is the set. So this set contains all the indices such that yi is equals to 1. So this is the set. This is the indices of positive examples. Okay. So for example, suppose you have here, right? So this will be the set U1. This will be the set U0. And how do you decide what is phi? The maximum likelihood phi will be just you count how many examples in total, 1, 2, 3, 4, 5, 6, and maybe 10 examples. And you say 4 of them are positive, so that's why phi is going to be, so in this case, phi will be 4 over the total number of examples, which is 10.4. And for some reason, I'm going to write this phi as follows. I'm going to write phi also just to, this is mostly just for mathematical, cosmetically, you want to make it look a little bit nicer in some sense or more consistent with the other equations I'm going to write next. So you can also write this as the following. Let me explain this notation. So this is so-called an indicator function. So indicator function, I'm going to write like 1 of e. I think in the homework we write it like this. You know, different people have different type of brackets, but it's the same as long as they define it. So 1e, this is equals to this is the so-called indicator function for the event e. So it's equals to 1 if e happens, and it's equals to 0 otherwise. So let me check whether this so in this case, right, so this indicator of y is equal to 1 just means that if y is equal to 1, it's equal to 1. This indicator of that is equal to 1. Otherwise, it's going to be equal to 0. So basically, this indicator is only 1 when the label is positive, and I'm taking the sum over all examples. So that's why I'm basically counting how many examples satisfy yi is equal to 1. So that's why this whole thing is just equals to u1. It's probably useful to understand this notation because I'm going to have a little bit more complicated formulas than this. So this is a warm-up in some sense. Go ahead. Right. This is just I guess in my mind, this is capital U, which is not the Greek letter mu. Yeah, I guess in the when you do it, handwriting is not that obvious. Yeah, but they're completely different things. Right. This is a set, and the other is a parameter. No relationship at all. Why do I? Sorry, I didn't hear. Oh, I see. So that's a good question. Yeah, thanks for us. So the absolute value is maybe I should define this. So this is the size. So when you have a set, I'm using this as the size or the cardinality of the set. Like how many items are in the set. That's just the notation. Yeah, that's a good catch. Maybe I should take a note on this. I think I was asked this last time as well. Yeah. Okay, cool. So I'm going to continue with telling you the solution of this MLE. So mu0, this is mu, not the u. This is the MLE for the parameter mu0. This is equals to 1 over, this is u0, the number of negative examples, times the sum of all the xi's in the set u0. So this is a sum over all the positive examples, and I'm taking sum of the input vectors, the feature vectors xi. So basically, this is just the average, the empirical average of xi's, of negative xi's. Right. So I'm looking at all the negative examples. I'm going to take the empirical average of the xi's in it. And that turns out to be the best estimate for the means of that class.
Empirical average?
Just
like does the word empirical have a different type of average?
Oh, I see. Good. Yeah, that good question. So it doesn't mean anything. Empirical average is the same as average. Yeah, there is, just think of it as the average. That's it. There's some reason why I use that, just because in some other cases, sometimes don't worry about it. Sorry. Yeah. Okay. So, any other?
So I guess these are the results you would get after solving those parameters and I'm doing this.
Right, exactly. So and now I'm just telling you the answer, but they sounds like very intuitive, right? So like, what would you guess? What's the best mean for this class? Probably you should just use the average of all the examples. At least if you see it, it sounds somewhat reasonable, and you can guess, just because these are symmetric, from the mu1 is the same thing. You're going to have 1 over the size of the positive examples times xi times the sum of this. Right? So this is the average of positive xi's. Okay, so and we're going to write this as, so I'm going to use this indicator function to write them in a slightly different way. So I'm continuing here. So if you look at this formula, you can write this as the u0, the size is equals to, as we argued, the indicator of yi is equals to 0. This is the number of examples where yi is equal to 0. Because y is equal to 0 means the indicator is equal to 1. Right? That's what the indicator is saying. Right? Indicator is saying is, if the indicator is 1, only if the event is happening. So that's why this is 1 when y is 0. So this is why. So that's why this denominator is the same as the size of the negative examples. So and then the numerator can be written as is equal to 0. So you first have this indicator only selecting those examples that are negative, and then you multiply xi. And for the second part, for the mu1 is the same. You just replace 0 by 1. So you have, and you select all the positive examples and you multiply xi. So why I'm writing it like this. One reason is that it looks a little bit kind of like more systematic. I'm not sure whether you agree with that. Maybe you don't. Another thing is that I think you see this kind of formulas pretty often for other cases as well. So it's probably good to unify them in some sense. But but you don't have to remember any of this. I think this way is the best way to remember them and kind of interpret them. So you just treat this as a cosmetic changes, some cosmetic changes of the formula. Okay, and next I'm going to have sigma. So the solution for the MLE for sigma is like this. This may sound a little bit complicated. Okay, so let me try to. So this is what is this mu? This mu is the mu we have computed above. So you have to use the mu you computed above to compute sigma. So these are the mu's you computed above. And mu yi could be mu1 or mu0, depending on what's yi. And one way to interpret this is that you just you can expand the sum into two cases. One case is that y is 0, and the other case is y is 1. So when yi is 0, so you have so those are the i's that are in the set u0, and this is xi minus mu0 times xi minus mu0 transpose. And then you have you look at those cases where yi is equal to 1, and then this mu yi becomes mu1, and you get this. So this makes it a little bit easier to interpret, because this, if you compare this with this is kind of the covariance, but the covariance evaluated on the empirical data. So this is on the data set you have seen. Empirical is a word that's used to stress that you are seeing the data, sample data. So I kept using that, but we don't have to use that word. So this is the covariance of xi's for those xi's in the set u0 for those negative examples. So this is the covariance of negative examples. And this is the covariance of the positive examples. And it turns out that the average of them in this sense is the best guess for sigma. Is the sigma that gives you the maximum likelihood. Okay, so I've got all of these parameters so far, right? So and now you're going to ask to prove all of these are true. But suppose we already got all of these parameters, we can compute them in numerically by plugging in this formula, because you just plug in all the xi's, you have all of the data, you plug in, you get all of these parameters. So you've got all the parameters. So that's the so-called learning process. You learn the parameters. And now the next question is, how do you make predictions on a new example? Right? You get the parameters, how do you make predictions?
the sigma is different for y equals 0, y equals 1. You take the average of like covariance for each class and use that to estimate.
So if you assume they are different, I don't think the formula will be this. And actually, if they are different, you don't even have an analytical form for the solution of the MLE. You cannot solve it analytically. So here it's kind of like, for some reason, because we are making all of this simplifying assumption, you can solve the maximizer of the MLE. But actually, it's not always the case you can write analytically. And when sigma are different for the two subpopulation, you don't have that analytical solution. Okay, so now we are talking about prediction. So given x, you want to output some y, right? You want to understand, whether this is a benign cancer or not, right? That's your final goal. That's the final goal of the problem. So, and the way that we do it is that you say, I'm going to output the most likely y. So I'm going to output argmax, the maximizer of P of y given x, and the parameter phi, mu0, mu1, and sigma. And note here that these are the solutions of the MLE. So these are not arbitrary parameters. So in some sense, you can even say I'm abusing notation a little bit just for simplicity. So here, this phi, mu1, mu0, sigma are those solutions that I computed from these formulas. Go ahead. In which case? In here? Okay. This is a matrix, right? This is a vector, this is a vector. Mu0 is a vector. Mu0 is the mean of the Gaussian. It's a d-dimensional vector. So, did I say something here? Okay, I guess I erase it, right? So you assume y given x given y is from this, from y is maybe 0. This is from this Gaussian with mu 0 and sigma. So mu0 is a d-dimensional vector. Sigma is a matrix. No, that's phi. Phi is a scalar. Is the probability of y is equal to 1, and mu0 is the mean of the mu0 is the mean of x given y is 0, and mu1 is the mean of x given y is 1. Yep. Okay, cool. So back to here. So this is my methodology. I'm going to take the MLE. So how do I compute this? So it turns out that this, of course I have to use the base rule to get y given x, because I only know x given y, I only know y, but I don't know what is y given x. So one thing is I have to use base rule. So let me do the base rule for you, and it's actually simpler than you may think. So because here you are maximizing over y, right? You are trying to output which y is more likely, right? Whether it's more likely to be benign cancer or not. So basically, this maximization problem just have two choices. You are just maximizing over two possible choices. So you are just taking the argmax of the two quantities, two scalars. They are both probabilities, and this one. So I just care about these two scalars and which one is bigger. And it turns out that these two scalars, their sum is 1, because given x, y can only be 0 or 1. So, right, so maybe let's suppose just for the sake of simplicity. So suppose you call this A and you call this B, then A plus B is equals to 1, right? And you care about which one is bigger, whether A is bigger or B is bigger. So if you have A plus B is equals to 1, and you are taking max of A and B, then what does this really mean? It really means that you are asking whether A is bigger than 0.5 or smaller than 0.5. Because you're going to choose A if A is bigger than 0.5, right? Because if A is bigger than 0.5, that means B is less than 0.5. So that's why you choose A. And you're going to choose B. Maybe let's write this again. Sorry. A, if A is bigger than 0.5, because that means B is less than 0.5. And it's going to be equal to B if A is less than 0.5, because that also implies B is bigger than 0.5. So basically, the question is that you just care about whether A is bigger than 0.5 or not. So going back to this, I'm doing an abstract thing, right? So if you're going back to this, then it really just means that this argmax is equals to 1, y is equals to 1 if the probability of y is equals to 1 given x, and the parameters is bigger than 0.5. Sorry, there's a little bit, and limited space, and if you 0 if p of y given y is 1 given x, the parameter is less than 0.5. So which also makes sense, right? Because y, oh my bad, right. So this also makes sense because basically this is saying that if the probability of y is 1 is larger, then you choose y. You choose 1. Otherwise, you choose 0. That's it, right? I'm just mathematically derived that for you. That's it. So and if you look at this figure, so what's the final decision? What's the final kind of like boundary between these two cases? This line will be the family of x such that this p of y equals to y given x is equals to exactly 0.5. So if you define this family of x's, right? This is a family of x's such that the probability of y given x is equals to exactly 0.5. And this is called the decision boundary. So, and on one side of the boundary, y is 1 is more likely. On the other side of the boundary, y is 0 is more likely. And the boundary, you just do some arbitrary type grouping, or you just randomly output. The boundary wouldn't be very likely to show up. It's very unlikely that your point will be exactly on the boundary. So it doesn't matter that much. So maybe let me just quickly, because we only have 2 minutes left, let me just quickly say what this decision boundary is for the Gaussian discriminant analysis, right? Because here, what I'm doing here is pretty general in some sense. You can see, right? I didn't really talk about what exactly the parameters are. And if you really want to know what this p of y given x is, right? You have to plug in the parameters. You have to use the modeling, right? So, and for Gaussian discriminant analysis, if you plug in, so what you do is you're following. So you do p of y is equals to 1 given x. This is the thing you really care about. So you use Bayes' rule. So you say that this is equals to p of x given y is 1. And here you only depend on mu1 sigma, and you have p of y is 1 given phi. and you divide this by P of x, the probability of x. This is the base rule that we kind of alluded to in the beginning of the lecture. So, and then you do a lot of calculation, which I think this is homework. You do a lot of calculation, and what you find out is that actually this has a relatively simple form. So the form looks like 1 over 1 plus exponential minus theta transpose x plus theta 0, where theta is something of Rd, theta 0 is a scalar, so they are functions, or they depend on, let me just simply say, these are depend on phi, mu 0, mu 1, and sigma. So basically, eventually you get mu, all of these parameters, and then use this parameter to compute theta and theta 0, and then you get y given x. And that's your probability. And then you want to compute a decision boundary. Let me also do that real quick. Sorry, we are running a little bit late. So then you get a decision boundary. So what's the decision boundary? The decision boundary is when this is equals to 0.5. And when this is equal to 0.5 is when this exponential is equals to 1, right? Then you have 1 over 2 is 0.5, right? So when the exponential is equal to 1, this means theta transpose x, I think, sorry, let me see. I think I need to have a parenthesis here. But anyway, because I'm abstract here, it doesn't really matter that much. So it means this is equals to 0. And you see that, P of y is equals to 1 given x is larger than 0.5 is the same as theta transpose x plus theta 0 is larger than, maybe I say larger than 0. So basically you have a linear function of x. That's your decision boundary. That's why I keep drawing a line here. From here, from the principle, you never know why this is a line, right? The principle says that maybe this is some family of x, right? That separate this. But the derivation tells us that at least for this case, the decision boundary is a linear function of x.
Is there any negative in front of theta transpose x?
So I think I'm going to have this. Yeah, sorry, this is a typo here. I should have the parenthesis. Yeah. Like, yeah. Anyway, the signs are not that important. I think, yeah, we are, maybe you can, what's the best way? You can come to me to ask the questions. I can stay here. Is that the best way? Maybe, yeah.